All right, good morning. Today we are going to talk about Kepler's laws of motion. Kepler has 3 laws of motion. We're going to go through the law of orbits, the law of areas, and the law of periods. So the first law is the law of orbits. He said that all planets move in elliptical orbits with the sun at one focus. So we got a picture of an ellipse at the top right over here, but I'm going to jump to the internet for a little bit more of a detailed picture. What you can see here is there are two foci. The sun is over here at 1, and over here, the opposite focus of the ellipse is over to the right. So there's a lot of geometry that goes onto the ellipse. We're not going to talk too much about it, but just some fun things to point out. The measure of how elliptical an ellipse is called its eccentricity. Eccentricity is this variable e. So what we can say is the eccentricity of an ellipse can be defined as the ratio of the distance between the two foci to the major axis of the ellipse. So essentially, how far apart are the two foci compared to the major axis of the entire ellipse? So what is the ratio, if you look in that little picture there, of 2EA over 2A? That E gives you your eccentricity value. The further apart the foci are, the greater the eccentricity. If the foci are on top of each other, that would be a circle, and the eccentricity of a circle would therefore be 0. So the planets are actually really close to circles. So if you look at all of the eccentricities for our planetary orbits, you can see right here, Mercury is 0.206, Venus is 0.0068, Earth is 0.0167, etc. Pluto is 0.25. So Pluto is by far the largest eccentricity. All the others are very close to circles, so when we do calculations, we can actually assume that they are circular orbits. We are simplifying it a little bit, but that's a simplification that we're okay making. All right, that's the first law. Nothing too crazy. Planets go in elliptical paths. The sun's one of the foci. Second law is the law of areas. What the law of areas says is that a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal times. So essentially, dA dt is constant. So what happens is, as the planet goes around, the line that connects the planet to the sun, so that invisible line there, will sweep out equal areas in equal times. So let's go to our internet. Let's get the simulation of that. Refresh it so it starts playing. Here's our equal areas. So that red line is the line that sweeps out the planet to the sun. What it's doing is taking the time to be the same, and the red is the area. So we can say it's all 1 month. It takes 1 month to go from each start to ending point. All of those areas are going to be the same. So why is this cool? What's the implication here? What's going on? Essentially, this goes into conservation of angular momentum. It is going to be traveling quicker when it's closer to the sun, and it's going to be traveling slower when it's further from the sun, but the dA dt will always be constant. That area in a specific amount of time is the exact same. So hopefully that seeing it live helped you. We'll go back here and we can write on here, this is true due to conservation of angular momentum. Conservation of angular momentum. All right, that's his second law. That's the law of areas. And then the third law is the law of periods. This one's a little bit of a mouthful. The square of the period of any planet is proportional to the cube of the semi-major axis of the orbit. So t squared to r cubed is constant for all satellites orbiting the same central body. So all of the planets, all of the moons in our solar system, t squared to r cubed is going to be the same. R, we said, was the semi-major axis, but again, since we have nearly circular orbits, r is really just the radius of orbit for the planets. So where did this come from? We kind of talked about this a little bit in the last video. We know that planets are going in a circular path. So the centripetal force is the gravitational force, which is going to equal mv squared over r. So G, mass of the sun, mass of the object, over r squared is going to equal mass of the object, v squared over r. Simplify that a little bit, you get v squared equals G, mass of the sun, over r. But since we're assuming circular orbits, we know the speed is 2 pi r over t. So I'm going to take this, square it, and plug it in for v squared, and I'm going to get that. G, mass of the sun, over r is equal to 4 pi squared r squared over t squared. And let's simplify this. Multiply t squared up, multiply r up, divide by g, m, mass of the sun. You get that t squared is equal to 4 pi squared over constant times mass of the sun times r cubed. Everything right here in parentheses is a constant. So essentially, the ratio of t squared to r cubed is constant. T squared to r cubed equals constant. Hey, that's what we said. That's what Kepler said. So the ratio of that for all the planets will be the same. My cubed is ugly. I'm going to fix it. There we go. R cubed. So what we can do with that is come over here and say, therefore, we've got this nice equation. Since it's a constant, t squared of a over r cubed of a is going to equal t squared of b over r cubed of b. So the a and b would represent the two planets here. We've got planet A, we've got planet B, we've got the distance A, we've got the distance B. Say I know A is Earth, and I know it takes 1 year, and we can say the distance is 1 AU, and then I know how long it takes Mercury to go around. I can figure out how far Mercury therefore is. This even applies with all of the planets and the moons in our solar system. So when Kepler was coming up with these laws, Galileo then said, hey, look, this actually works for the moons of Jupiter too. And all of a sudden, all scientists were like, wait a minute, we actually have a heliocentric universe and not a geocentric universe. And people accepted Kepler's laws, and it was kind of like a big turning point back then. So let's go here. We can see one more thing. I think the third law is just ridiculously cool. If you plot it, so here's actual numbers for it. If you plot the cube of the semi-major axis on your y-axis and the square of the orbital period on your x-axis, you will get this nice linear relationship. That straight line shows Kepler's law of periods. Technically, we can say down here, if we have the following units where the period is in Earth years and the distance is in astronomical units, where 1 AU is distance from the Earth to the Sun, then t squared over a cubed is just 1. You can do that for all the other planets, keep it in those terms, plot them, and you get a nice, pretty graph like that. If you want to just think about the numbers, here we have, if you look at Earth, the semi-major axis is 1.5 times 10 to the, 15 times 10 to the 10th meters. The period is 1 year, so you get 2.96 if you take t squared over r cubed. And you can see all the values for all the other planets. It's all essentially 3. You get the same value for all of them, which is awesome. It's crazy. Craziness. Science is fun. All right. Go back to the notes. Whoops. Where'd they go? That's not your notes. Why'd they go away? Chapter 15, video notes. Here we go. Back to them. I don't really have anything else to write. Hopefully that all made sense. If you have any questions or you want any more clarifications or you want to go into more detail on something, just let me know. Send me an email, whatever. Hopefully this did make sense. Awesome. All right. Have a great rest of your day, and I will talk to you guys again later. Bye.